Hello ladies and gentlemen, and welcome to a new episode of how to use our AIMS, AI management system, to create a trading bot. Okay, thanks a lot for checking the videos all about the trading, because this is the most viewed content, if I can say so. People are really interested in beating the market, as always, right? I know the struggle, and I also know how it feels, and it's just crazy sometimes what you're willing to do to find another way in trading, and I really like it. So what I want to do right now is show you how to create a trading bot that can do a price regression. That means in this case, we won't predict if it's a good idea to buy, hold, or sell. We try to predict the exact price for the next time frame. So let's start over. First of all, you will have to import a dataset. I will support your dataset. That's it. There is nothing more than a CSV file from an Excel or whatever. As far as I know, it comes from Duca's copy, and it represents the euro US dollar currency pair. So pretty famous so far, right? It contains of about 2.2 million examples and about 11 columns. So it means one column represents one feature. A feature can be like an open price, a high price, close price. Now it's imported. I double clicked on it, and you can see here the columns. Like I said, there are some other features: intraday, bar number, day of week, whatever. And here you got a preview. Let's go ahead. You can go analytics, and you see some information about the data that might help you later on. If you get capabilities, you can also use a wizard. We created a wizard that it's just like, you don't have to go through all the different nodes. It's just like click and go. You choose some information, and the AI building process is automated. But we will start this all from scratch. We create a new project and name it like trading euro US dollar. Okay. Double click on it and start over with the data selector, because AI is nothing more than a model based on historic data. We try to model our world everywhere. If we search for a cafe, for example, and we know the city, we know anyhow where it is, We don't know exactly everything, but we don't need to. The model is just sharp enough that we find the cafe if we have ever been there. So that's what we do here. We pick out a small amount of information, depending on this currency pair here, and it's not everything. There are no news inside these columns. There is a lot of information missing regarding the market in general, right? But we try to focus on this small part of information and try to get a good estimate on modeling an AI that is capable for trading, to use it for trading. So first of all, what we see here is the preview. We got a date column. We will kick this out because we can't make use of it. Open, high, low, close. We got volume, and then we come to like high, low range. This is a column where you find not a number values. Not a number values can't be used. So what we use here is drop NA. That means we drop values that are not usable. If you use like the 0, it will drop rows, but we want the node to drop columns. So we double click here, press 1, search for all the columns, and it works like this. If there is anywhere in any field or part of the table, there's anywhere not a number value, it will kick out the whole column. Okay, because if we don't do it, there will be errors later on. So now it searches for the number values and yeah, drops them. It shouldn't take that long. So we are kind of done. You see we had 11 columns here, now we got like 9. That means this and this column has been dropped because there have been a lot of not the number values. Now what we need to do is drop column, because we also want to drop the first one, because it's not encoded in a way that we can use it. You know, if the date would have been like 1, 2, 3, whatever, we could have used it, but this format is like random, it's a string, you know, we can't use it in this case. There will be features to transform it later on, but not yet. So we proceed here, and afterwards we will have a table with like 8 columns, and each column with like 2.23 million examples. This table is in a chronological right pattern, so that means from the bottom to the top there is it is sorted in a time way, right? That's important. You can't just use random data the way we do it here. We need the data to be one after another. We can make it visible if we do a data plot, for example, and I would just choose like you don't have to fill in the columns for X data, it will just count up, right? And we see like the open price, and I make a line like the first 1000 values, and then I want to have a plot. You can combine the values like open, high, close, whatever, and use different ranges, but okay, what we have here is right the price. I don't know when it was. If we have a look, the first one was 2017, January the 1st, and then yeah, it dropped a little bit. Okay, you see? Now you know what the data is all about. It's just about prices. Okay, so first of all, we should ask ourselves, what do we want to predict? If we have a look at the table, we got like open, high, low, close, okay, and to make it faster, it would be a good idea to drop even more columns, okay? Open, high, low, close, yeah, it's important, but I could like drop open, high, and low and just use close, okay? Use the last close value to predict the next close value. For example, the last 100 close values to predict the next one. The time frame is also important. This data here, it's not from me, seems to be minute-wise. That means one entry is 1 minute. Okay, you could also use data based on days, hours, and so on. It's your choice. This time it is all about the minutes. So, okay, what do we do next? Now, usually we would like, I just restarted the video, so there is the preview to go again. Now we would start over with scaling. So again, what is scaling? Artificial neural networks seem to learn better if the input data is scaled. Okay, that means, just let me pick it out. Scaling, where are you? Here, kind of blind here. Okay, so scaling, we give it a name. Scaling means neural networks tend to be better in performance if the input values don't lie too far away from each other. Like, okay, everything is between 0 and 1 or 0 and 100 or whatever, but not like, okay, this feature is between 0 and 1 and another one is between 0 and 1 million, you know, because it's trained by gradient descent, and the gradient is bigger on the features with a wider range, you know. So while training, these features might get more attention than they really have regarding the data. So we name it here, scale trading, and like 0 and 1. Min-max scale means, okay, the scalar is based on each column. Okay, for example, if we take volume, the biggest volume is, let's say, 5. The smallest one is 0 because no one traded. So if we rescale it, then 5 will become 1 and 0 will stay 0. Okay, it's a rescaling in the min-max range of the feature itself. We choose all the columns and proceed. So this might take a short amount of time, and we'll scale the whole data. You will see it here, and I will also pick out some analysis. A box plot, I always use this because it shows pretty nice what is scaling all about. Okay, let's do a box plot. We just print all the features. These are all numerical features, so we can plot them with a box plot. If there is a categorical feature like man, women, or green, red, blue, you can use this plot on these features, right? So you see all these features are in a small range, and volume is going to a maximum of like 69,000. So after scaling, we use the box plot again. You will see all the features are in the same range. Okay. So let's do it. Just a second. Okay, you see it here right now. Everything in between 0 and 1. Now we can go ahead. And as I said, I would like to drop also 3 more columns to make it easier to calculate and be faster and so on. And what I drop now is like open, high, low. I know these values are important. Okay, I'm pretty sure high and low indicate the range that happened in the last minute. Okay, and it's an indicator for also the volume, trading volume, how the price is behaving and so on. But I will do it like this to make it faster, make it more comprehensive, I think. So because now we will go to the so-called sequentializing. Okay, that's the thing most people don't understand quite well. Imagine, I will describe it when I started the sequentializer because it will take some time. We give it a name, sequentialize, and name it like, let's say 50. The 50 stands for a window size. I will tell you what this means. We include the targets. The target is close. So what does this do? Well, if you want to trade, what are you doing in the first place? You open up a chart and have a look at different time frames and check, okay, how was the stock price behaving in the past? Okay, like in this graph, you see the last 1,000 opening values. Okay, so you seem to get a feeling where the price is moving. It has dropped, okay, it's just a snapshot, sure. But we always do this. We look in the past, have a look at the past, and decide, okay, is it maybe a better idea to buy or to sell? And then ask ourselves, okay, on what kind of time frame? Buy on a time frame of next 5 minutes, or sell on the time frame of the next 5 days, you know? So you have to decide this. But the algorithm will also have to work like this. Right now we chose a window size of 50. That means we take the last 50 values. Okay, this is a pattern, a time frame, and feed it to the neural network. And what we predict then is the 51st value. Okay, the last 50 values are the input, and what we want the algorithm to predict is the 51st. So for the next minute, because we don't know what's happening in the next minute, and we try to use an algorithm to predict it. Okay, so what I've done here is just using the sequentialize node to do this for me. It will now go through all the data. I will do this here to make processing faster, because the program itself is working as a browser window, and the more there is to render, the slower it might get. So I just clicked it in, and now it will take some time to complete the sequentialization process. If this is done, I will show you how this has been done. Okay, now it's done. It took like 5 minutes, because you have to imagine we take like these 2.2 million values, and from 5 columns we create like 250 columns, because all of the 5 features that they are left will be used 50 times. Okay, so now you got like 1, 2, 3, 4, 5, and so on values in the top. That means, okay, these are the time frames I have talked about, and the last one is the target value. It's the 51st value you want to predict. Here you see it's the 50th value, but this is just because we start with a 0. Okay, now before we can start creating a training, we will have to choose a splitting. We will split the data like this, for example, and choose mode normal, because we don't want to have shuffle inside. We don't want to use data from the future to make the AI algorithm capable of knowing what is going to come. So we choose normal. No random seed is required. We just click proceed. After around about 5 minutes, the training node has done its work, and what we have now here is we made out of this one data set 3 different ones. One that contains 70% of the data, that's the train data set. One that contains like 20% of the data, and the test data set for checking out in the end. Okay, so now we have to create a neural network architecture. And how will this architecture look like? Well, we got like 250 input features and 1 output feature. That's what we have to mention. So let's go to the architecture modeler. Well, we create a new architecture, trading Euro, US dollar, and double click on it. First, there's playing ground. We need an input. The input represents what we get from the table. So you see here like 3 parts. We have to click on minus because we just need this one here. And what you have seen, what I've mentioned right before we got here, is like we got 250 input values. Okay, and this is what we put in here. When we now choose a so-called dense layer, then we can combine these two, and this means this dense layer is fully connected to the input. What I do now is just from my experience. I combine 250 nodes to this input layer and choose the activation function ReLU, because ReLU is really fast calculating. You can also try Sigmoid, might be more exact, and other ones like CLU or ELU. So afterwards, from my experience, what helped a lot is to choose on the left side layer normalization. Normalization is a technique that helps the neural network to generalize even better and learn better. So I will choose now again a dense layer and then a layer normalization layer and so on until we have broken down what we want to do. From my experience, I usually create a network, a dense network, in a way that I have a part inside where the amount of nodes in this place here, 250, is going up and then strictly going down. Like I would choose like 300 here, okay, and use layer normalization again, and then go down more drastically, like 111, okay, and choose another layer normalization right here, and again go down even deeper to 17, for example, and then choose the last layer, that will be 1. And for the last layer we have to choose a linear activation function, because this will be our prediction layer. Now we've created a neural network and we can save it. If you click on layout nodes, then everything will get in order and you can save it now. You have to wait a short amount of time, okay. You get this message like, okay, it could be compiled. That means the program is checking if your neural network, like you did it here, is working before we go ahead. So now let's go back to the project and we will choose an architecture node and a training node. So first we choose the architecture we have created here, and we put like train and validation where it belongs, and the architecture too. What you see here is input is 250 and output is 1. Our columns are 250 and 1. As I said, you got 250 columns as input, and this last one is what we want to predict. The sequentialized node has already prepared the data in a way that the last one is always the next time step, so you don't have to care about this. We give it a name. I will choose the name I have already chosen for the project. Choose like, from 1000 epochs might be too much, but we can stop it anytime. The loss function, as loss function we can choose mean squared error. This fits. And I will choose train on CPU in this time, see if it works out. This is something you can choose too if you don't have the capabilities to train on a GPU. And then we choose a data option. Don't know how much we can fit into our random access memory. Just like, let's check if 512 might be okay. And now we have to choose the target. We can scroll like hell here, okay, but you can just type in close and then scroll. You will find the last one, but you have to delete what you have written. So now you have chosen the last column. Here you got something to choose. Shuffle should be always on. Cache means while training, the algorithm is saving the data and random access memory to train faster after the first epoch. You can use this, it's quite helpful, but if the amount of data is too high, and your random access memory is not big enough, it might break up. So this is something we don't need here. Optimizer will be ADAM. It's always a good choice, and we choose like an initial learning rate of 0.001 and keep it constant. So let's just try if it works out. I don't know if you can see my setup and how it's performing. We will see when the process starts. Right now the software is preparing the data. You will see when training really starts. It's not happening yet. So you can have a look here in your random access memory. In Germany it's called Arbeitsspeicher, just to be sure, and you see it is rising, right? If you don't have that much, just choose a smaller batch size. Okay, this will help a lot, pretty sure about that. But the training still did not start yet. If you want to have some additional insights, you can go to the location where you have installed aims and go to logs. There is a server, job manager, and worker log, for example. If you choose the worker log, okay, and scroll down, it has started training yet. You've seen it on the CPU, and you see, okay, this is the neural network, and you see there are 174,000 parameters, and you can see what's happening inside. And now you see also the training started, like all the cores are used, and you see how fast it goes. The first epoch is a little bit slower than the others, as usual, because we have chosen the setting cache. So after the first epoch, it should be a lot faster. Let's see when we are done with the first one. And if there's something to learn, you will see if the losses shown in the training history drop, then you know, okay, the data contains information that leads to an AI learning about what you wanted to learn. If the losses are not dropping, then it might be the case that the data you have served is not containing information to solve the problem properly. Okay, so now it should be a little bit faster, and all we have to do right now is waiting. So we got like 2 epochs here. You need at least 2 epochs to see lines in here, right? I will switch to train on GPU to see if this is faster. If you change something here and want to continue the training, then just click on continue training. If you click on process or proceed, it will start again from scratch. I now have chosen the algorithm to use both graphics cards. Let's see if this works out, and then we will see if this is going to be faster. CPUs are in use too, because they have to prepare the data, right? But not that much when you use the GPU for training. Now all this stuff is happening again. The random access memory is rising because the data is prepared. I mean, we got like more than 2 million data points for the training data set. It's all about I think 1.5 million or something. But it's a lot too. And yeah, it's going to be prepared, and we will see how fast it is compared to like 24 AMD Ryzen Threadripper cores. So, as you can see here, the training started. You find something wrong information, epoch 1, because until the first epoch is done, it won't know, okay, it is training further. So now after the first epoch, it knows we are already in epoch 3, and you see it's a lot faster than if you choose training by a CPU. Before this, we were like used like 1 minute for each epoch, and now it's like 10 seconds or something like this. And you see like the losses dropping. You got two losses here. We got the validation loss and the training loss. That means the training loss is the blue one. This is the data we use to train the model, and the validation loss is just data that has been sent through the trained model after each epoch to see, okay, how good is the model performing on data that has not been trained. So we'll let this run through until we see like nothing is changing anymore or something like this. We can then hit stop and do something else. So it seems like there is not really that much to learn anymore. I mean, it drops still, but I don't want to go deeper into it. I stop it right now. Okay, what do we have now? So we have a model. Let's just save it, and you can go here to models, and you will find it here. If you double click on it, you see some meta information and the training history. Let's go back. So what have we done until now? We have created, we have transformed data and created an AI model that might be able to predict the price of the euro US dollar currency pair for the next minute based on the last 50 minutes. So now what we have to do is we have to check it. Evaluation is always really important. So we use a prediction plot. That means drag and drop. We make a prediction. To do so, we need the model we have trained and data to predict. Okay, so we go like this. Okay, this takes too long because these are like 220,000 examples. I will just split up the data set again to make a short example. This time I use shuffle. and yeah, just 1% will be enough to show it. You can always use data splitting if you want to, and I use the test data set, a small part of it, to make a prediction then, because this takes too long for me right now. I don't want to wait anymore, so I just split up some data and use just a small piece of this data for predictions. I mean, I could have done this also here. I mean, before we trained, I could have switched like this one to 80%, okay, and here just 99%, so that just 1% will stay test data. But I have not done that. So now we got like 2,200 examples we want to use, and we will do the prediction. Again, the prediction consists always of a model that has to predict something, and the something that has to be predicted, this is the data, you know, and the data input structure has to be the same for inference, that's what we are doing now, as for training. You will always have to have the same features and the same, how is it called? Just let me check. Same sequence, as in the training examples, so that the algorithm can learn, okay, when there is an activation, this might be something, right? And if you switch up the sequence, neural network will not know about it. So now we have made a prediction. It's just a data node, if you want to say so, and we use a prediction plot to plot the predicted data. You can just hit proceed, you don't have to choose the targets, and then you will see two kind of points. Blue ones, I think, are the ground truth, and the orange ones are the prediction. So as you can see here, this is how the model performs. You can't really see quite good the blue line. The blue line is the ground truth. Okay, I can make it bigger to make it more visible, maybe. Okay, and now you see, okay, for example, this case here. This was the ground truth and the prediction was slightly higher. It seems like it is slightly higher close to everywhere. And then you got like these parts here, the prediction was really bad. This could be because, for example, first of all, this plot is sorted by size. That means if this plot was sorted by time, you would have points all over here and you were not able to see, okay, which point belongs to, which point of prediction belongs to the ground truth. And in this case, you see how close they are to each other. And why we have this upper here could be because the test data lies in the near future, and the training data lies in the past, near future, sorry, near past, and the training data is older, like 2017. So maybe in the training data set there is another range of price in between euro and US dollar represented that is in the test data set, you know. So like if you have never seen a cat, you might not know how a cat looks like. So it's always good if your training data set is broad. It consists of a broad range of features, a broad range of values, not only a small, separate area. It should consist of a broad range of information. Okay, but what does this say? It's easy. It says, okay, In this example, where you have some kind of input features, the ground truth was 0.69 and the prediction was, let's see, 0.6919. And you might ask, okay, what does this mean? Yeah, this is the value that is scaled. This is the scaled value. If you want to have the real value, you have to backscale it. Okay, therefore, I want to show you this last thing. You can choose like the scaler again. Okay, you use the scaler right here, and you just scale close, and you just choose the column close. Okay, you scale this, and when it's done, you will have saved scaler in the software that is capable of scaling this specific column back and forth when you need it. I will show you soon when the scaler has done scaling. So if you do it like that, you will see all the other features are not scaled, but the close feature is, right? There you can see it. Now, for example, you have made the prediction. Okay? You can go to transformers and say reverse transform. So you take the predicted data and use the scaler we created right now and scale close. Now the scaler should scale back. Voila! The scaler backscaled the data. If you have a look in comparison, I pull it down and do it like this. You see what was 0.71 before is now 1.16. The original value again. We need to do this also for the input data. We reverse transform it. Okay. Here we choose this scaler and close. But the last one. Okay, proceed. And this is the predicted data. I put it here. And this is the true data then. Put it here. And you can choose the prediction plot too. This is the predicted data, this is the true data. And see what's happening. Now we are plotting the same plot like here, but the difference is that the axis is scaled because the original scaled data is scaled back now. It's a little bit laggy. That's because I already said that this is a browser window and it tries to do everything in real time, and plotting like 2000 points might be hard, but it's even harder to plot like 200,000 points. So be cautious if you do so. So now we got the real axis, if you want to say so, and if you want to check like this point number 247, the prediction was the currency pair has a price of 1.1547 and the ground truth is 1.1553. I can't tell if the difference is too big. I mean, the model will never be pretty good because, in this case, because the data is not broad enough. I mean, we got a lot of data points, but I think the 5 chosen input features are too few. Okay, that means what have you used? we have used, like before sequentializing, there were just close, volume, intraday bar number, day of week, and a simple moving average. I mean, that's not much, right? And what I can suggest is try out more features, try different indicators. You can also ask in the comments about different neural network architectures. I will make videos specified on your requests if you wish to talk about different architectures, data insights, whatever, we can talk about it. So, and if you want to see how to integrate this trained AI into any application via an interface, I can make a video about this too. So that's it from now. I hope you learned some and wish you all the best. Have a nice day.